Alright, we're back to do 4, 5 and 6. That should be number 4 there. 4, 5 and 6. Number 4, find the critical angle for your sample of perspex practically using the light box, then calculate it theoretically. Okay, so 2 parts to this question. Chunk of perspex, beam of light. Remember, the critical angle is where the beam of light doesn't escape from the denser medium. Okay, so that's past the critical angle. We need to go less, okay, and that's less than the critical angle. Right, so what we need to do is we need to get to the point where it, sorry for bumping that, where it refracts and runs parallel to the surface. And let's say that is pretty much it. Now, we need to be careful here. This is the point where the light emerges, and this is the point where it goes in. Okay, you can see that under the block. What we really need to do is we need to trace this line here. Obviously we can't because it's under perspex. Don't be tracing this light here because this incident ray has gone in, bent, then bent again. So it's not this angle. That's going to give you a wrong reading. It's this angle here. All right. Okay. So perspex out of the way, and we join those dots, and then of course we need a normal. So let's get our protractor back over here. Set it up. So it's 1 line. 0. There's our normal, and I'm calling this my critical angle. That's a C for critical. Alright, so what is it? Sorry if I keep bumping the camera. I'm trying to look straight down on top of this to try and get it as accurate as I can. Alright, that's 42 degrees. 42 degrees. Okay. Put an arrow on it, and my refracted ray is basically running along the top there. Okay, so I found it practically. I think that practically our critical angle is 42 degrees. Now, let's calculate it using information collected from our previous workings, which was we found that the absolute refractive index of our bit of perspex was 1.42. So N perspex equals 1.42. N of air will need to be 1. Alright, to calculate our critical angle, the sine of the critical angle equals N2 divided by N1. Alright, this is a derivation of Snell's law. So, don't forget that in this situation our ray of light has gone from perspex to air. So this is N1, this is N2. Alright, so N1 perspex 1.42, N2 is air. Don't get that mixed up, otherwise you're going to get an error on your calculator and you're going to wonder how the hell you get an error for a number. Okay, 1 divided by 1.42 equals, so the sine of the critical angle is 0.7. Alright, to get the critical angle by itself, we do inverse sine. So inverse sine this, get rid of this, but then we need to inverse sine this side. 44.8 degrees compared with 42. That's alright. That's alright. A couple of degrees out. It's to be expected. So we'll go with that. We'll go with that, no problems at all. Number 5. A ray of light passes from air through perspex back into air. Find whether the ray of light in air before entering the perspex and after exiting the perspex is parallel. Now, to explain what that question is asking, what it's asking is, if we go back to our situation here where we had our block of perspex and our ray of light going through, it's asking whether this ray of light is parallel to this ray of light. Theoretically, it should be. Right, with our refractive indexes, whatever the amount it bends from here to here, the opposite should happen here, because the refractive index of this air over here is 1, same as this. So, we know that this ray of light makes an angle of 28 degrees to the normal. Let's find out what this one does. Sorry, while I fit all this around. So now, I measure this angle, and I find it to be 27 degrees. Alright, and 27 to 28, yeah, again, happy with that, that's close enough for an answer to number 5 to be, essentially, the answer is yes. Right. That the ray of light in the air before entering the perspex and after exiting the perspex is parallel. Right, 28 degrees to the normal, 27, we're happy with that. That's close enough to being parallel. If my measurement's more accurate, I'm sure these would be the same. Alright, moving along to the last one, number 6. Demonstrate and describe dispersion. Which of the 6 colours that make up white light bend the most and the least? 6. Dispersion. Alright, well, when we're looking for the critical angle, we already were able to see a bit of dispersion. And that's that there. We can see a breakup of colours. So, I think the first question was demonstrate and describe dispersion. Well, that's the demonstration of it. Describing it, well, it's the bending of the individual colours of white light. So white light's made up of all these colours here, and due to their different wavelengths and different frequencies, they bend to different degrees. That's why you get this dispersion, this breakup into separate colours. And if we're able to break them, to funnel them back in together, we'd get white light if we were able to get these to all converge back in together. Which of the 6 colours that make up white light bend the most and bend the least? Well, it's pretty easy to see. We know that our colours are Roy, G, B, V. So we've got red on one end, violet on the other. Well, we can see that violet's down here bending the most and red's up here bending the least. So I do have a tiny bit of time left. Let's see if this makes any difference. No, maybe not. Either way, it's clear to see that this is much more down the blue end of the spectrum and this is much more up the red end of the spectrum. So, violet's bending the most, red is bending the least. And I think that answers the question. Cool, we are done.